So there's another type of characterization tool you can use called neutron diffraction. That's based on diffraction of waves. Remember, diffraction is all about the scattering of waves off of objects. In our case, we're interested in atoms, right? In XRD, X-ray diffraction, you're using X-ray photons. Okay, so you're using light, and you're using light because light interacts with electrons. Okay, to scatter off of electrons. That's how you're probing. Basically, the valence electrons of the atoms are doing the scattering. Okay. In neutron diffraction, which is a complementary technique, you're using neutrons. Neutrons are much bigger, and so they're like bowling balls compared to electrons. So they're just going to penetrate through all the valence electrons, the core electrons, and what are they going to scatter off of? Only something that's about their size, right? So they're going to scatter off of nuclei, because nuclei contain, well, protons and neutrons. And so as a result, XRD is sensitive to heavier elements. It's not very sensitive at all for hydrogen. Okay, in fact, you can't really get hydrogen positions at all because hydrogen only has one valence electron. So the probability that you're going to scatter off of a hydrogen atom is very low. Helium, we don't really talk about because it never forms compounds. Okay, and lithium is the next one. Lithium can be difficult. There's usually a pretty large degree of uncertainty of where the lithium is. Once you get to beryllium, there you have four electrons. There's enough to say with pretty good certainty where beryllium is usually in most XRD spectra. But especially when you have like a lithium next to a lead, let's say like a really heavy atom, the lead can kind of drown things out, right? Because it has such a high scattering cross section compared to the lithium. So this is where neutron diffraction is really useful. It's really useful, particularly for hydrogen, because the sensitivity turns out to be sensitive, to be similar for all elements. All elements have a nucleus, so it can do this scattering, and electrons aren't as small as electrons. Now the interesting thing about neutron diffraction, right, is you're thinking, well, neutron doesn't have a wave, right? Or this is all about wave optics, right? Diffraction. Well, neutron does have a wave. Okay, everything has a wave. Remember, de Broglie wavelength. All mass that's moving acts as a particle and a wave. This is the crazy nature of the universe, and the wave-particle duality, not just of light, but of everything. Okay, so we use the de Broglie relationship, right? Lambda, the wavelength of anything, is equal to h over its momentum, m times v, the velocity. So in order to get the proper wavelength, okay, you want a really small wavelength. Remember, you want a wavelength of the order of nanometers in order to probe atoms, atomic spacing, because that occurs on the order of nanometers, right? So in order to do that, you want V to be very high, right? So that lambda is small, okay? And so how do you get high speed neutrons? How do you shoot high speed neutrons at a sample? You make them in a nuclear reactor, okay? A high power nuclear reactor. And so because of that, it really takes specialized equipment to generate these high speed neutrons. But it's the exact same principles as what we discussed in the previous videos about XRD, Bragg's law, all that stuff, okay? But there's really only a few places in the world where you can go get these special neutron diffraction experiments done. You have to be usually at a national lab that has nuclear reactors, right? But otherwise, very, very useful technique, especially if you have hydrogen in your sample and you need to know where the hydrogen is with atomic level precision.